everyone, welcome back to ResEcon 313. In this class, we will look at chapter 14. So in chapter 14, we're going to look at something called decision diagram. Okay, just to put things into perspective, this is sort of a roadmap of what we've been doing in this semester during our classes. So very early on, we looked at what is a probability tree, right? So in the probability tree, we're looking at different distinctions. And then later on, we developed something called relevance diagram to represent the relevance relationships between two distinctions in the probability tree. Okay, over here, the first distinction being weather, and there are two possibilities of weather, which is sunny or rainy. Then the second distinction is called rain detector's message. And there are also two possibilities in terms of what messages you can read from the rain detector, which is either a sunny day message or a rainy day message, okay? And the weather is obviously relevant to what message the rain detector sends. And this is a good, useful rain detector we're looking at. We know they are relevant to each other because depending on different weather, the probability that the rain detector reads sunny is different, 0.8 versus 0.2. These two conditional probabilities differ. That's how we know that weather and the rain detector's message is relevant to each other. Then we use an oval-shaped thing to represent the distinction of weather, and we use an oval or a round-shaped thing to represent detector. We use an arrow from weather to detector to represent the fact that these two distinctions are possibly relevant to each other. Again, these are the things that we've learned in the first half of this semester's classes. So we construct a simple, clear, and concise relevance diagram to represent the relevance relationships in the probability tree. Then later on, towards the second half of the semester's classes, in recent classes, actually, we learned something called a decision tree. Now, comparing the decision tree with the probability tree, we're noticing that it is richer in a very distinct way that we include some nodes that represent a decision node. And then all the branches out of the node represent alternatives of the decision. Okay, and this is a decision tree for the party problem without any rain detector or clairvoyance message. And what we're going to do in chapter 14 and in today's recording is to represent this decision tree also with a diagram that is just simpler to read. Okay, just to give you a preview of our sort of ending product from this chapter, we're going to use a diagram like this to represent the decision tree, okay? But I just want to make it clear that the relationship between decision diagram and decision tree is just like the relationship between relevance diagram and probability tree, merely a very concise and sort of a sketchy way to represent the information we have in the decision tree. Okay, so this is what we will be looking at, and I will explain each and every shapes in this decision diagram to you, what they mean. And also, I will explain to you what these arrows mean in the decision diagram, okay? Like I said, the relevance and decision diagram share some similarities. They are both some simple communication tool. They will be useful to help you to improve the clarity of thought. And they're both compact than the corresponding trees. Decision diagram is more compact than a decision tree. Relevance diagram is more compact than a probability tree, okay? But there are always some differences between the decision diagram and the relevance diagram. One thing that you noticed in the previous example is that there are more shapes in the decision diagram than just the oval or round shapes. Here we have a square, and here we have another stop sign shaped thing. And another thing is that depending on the arrow, the destination and the origin of that arrow, it may have different meanings, and you need to interpret the arrows in the decision diagram based on where it comes from and where it goes into. Okay, so we will look at the first thing first, which is the different types of nodes or the different shapes in the decision diagram. Then we will look at the different meanings of arrows. Then finally, in the last part of today's class, we will represent different decision trees that we have been looking at into proper decision diagram. Okay, first topic, different nodes. Okay, as one thing, one common node that decision diagram has with respect to, similar to the relevance diagram, is that you of course have the uncertainty node. Okay, it's still represented by an oval shape or a round shape if you wish. Okay, and the representation of uncertainty or the representations of distinctions are exactly the same as in a relevance diagram. Okay, you will need to give a name to the uncertainty node. You will have some rough descriptions of it. In order to complete the description, you will need to make sure that the different possibilities of the uncertain node passes the clarity test, and also importance, how many degrees are there, what is the name for each degree, what is the probability that you assign to each degree or to each possibility, and then what is the time that you're looking at. Okay, all this information need to be completed in order to fully describe an uncertain node in the decision diagram. And also similarly to what we have seen in the relevance diagram, a distribution is always conditioned on the background knowledge. The distinction is always conditioned on background knowledge. And also it is conditioned on any nodes that have arrows entering this. So if you see one distinction receiving an arrow from the other one, then the distribution represented by this uncertainty node is conditioned on the other uncertainty node that is sending arrow into it. Okay, this is just everything is the same with the relevance diagram. The second type of node you would see in a decision diagram is of course the decision node, right? Without it, you wouldn't have a decision diagram to start with. So the decision node represent what kind of decisions are faced by the decision maker. Again, it is a higher level view, meaning this decision node represent all the alternatives. Okay, in order to describe a decision node, you need to give it a name, such as party location decision or rain detector purchase decision. And then in order to describe a decision node completely, you would need to give a definition and explain the importance and give a list of alternatives that a decision maker can consider at this decision node. Then you need to clearly define what each alternative means, and also you need to make sure we know who's the author of the decision, who's the decision maker in some sense. Okay, and a third type of node that you would say in a decision diagram, not always but sometimes, is deterministic node. Okay, so when we say a deterministic node, we are referring to this node rather than these two. Okay, this is a deterministic node. It is an oval shape or a round shape, but with double lines as its edges rather than single lines, okay? So over here, we have a deterministic node called fxy, and there are two uncertainty nodes sending arrows into it, okay? So this deterministic node represents a deterministic relationship or a deterministic observation. For example, this node could represent something called profit, and then this node could represent something called revenue, and this node could represent something called cost. You are uncertain about the revenue. You are uncertain about the cost. But once you observe the revenue and the cost, you will be able to determine what is the profit for sure, okay? So that is why we're using the deterministic node to represent profit, given that we know what is the revenue for sure and what is the cost for sure, okay? So again, here the revenue and cost are uncertainty. That's why they are represented by a single line oval shape. However, profit is certain, is very 100% determined by the revenue and cost, okay? Just like using this very common calculation formula. However, if you don't know the revenue and the cost, meaning if you don't have revenue or cost sending arrows to profit, then profit becomes uncertain. However, in this part, since we know revenue and cost, profit becomes a simple calculation. It removed all the uncertainty that we have about profit once we know what is the revenue and what is the cost. Okay. Here, this would be the proper way to represent this relationship. Revenue, uncertain. Cost, uncertain. After you know the revenue cost, profit becomes certain. Okay, there's no doubt about the profit anymore, as long as you know revenue and cost for sure. Okay. If we know the inputs into a deterministic node, there is no more uncertainty at that node. And the last type of a node is called a value node. It's also a special, you can think of a value node as a special type of deterministic node. Notice the similarities between value node and deterministic node. It is also a double-lined shape. However, it is no longer oval, but like the stop sign shape. Okay. It is similar to other deterministic nodes. It is completely determined by inputs. Once we know the inputs, there's no doubt about the value. The difference between the value node and the deterministic node is that the value node represents the value that the decision maker is trying to maximize. You can think of a value node as the goal of the decision maker. For example, if you're trying to maximize your utility, or if you're trying to maximize your profit, then in that case, we can use this node this shape of value node to represent profit. If we're looking at, say, a firm's production decision, then the goal for the firm is to maximize its profit. In that decision diagram, profit would be marked with a value node rather than a deterministic node. Okay. So the nodes that are, you see in the decision diagram is pretty straightforward. There are just 4 types of it: the uncertainty node, the decision node, a deterministic node, and a special type of deterministic node called the value nodes. So you would differentiate each node by their shapes. Okay, if you see a shape, an oval shape, a single-lined oval shape in a decision diagram, you would know it represents something uncertain. Okay, it represents a distinction. if you see a double-lined oval shape in the decision diagram, you would know that that distinction is deterministic. There's no uncertainty about it. Okay. And then the next step to sort of define or to draw a decision diagram is to make sure you know what the arrows mean in the decision diagram. The meaning of an arrow is determined by the origin and destination of it. In order to make sense of what each arrow means, you need to look at both where it comes out of and also where it goes into. And then depending on the origins and definitions, there are 5 types of arrows in the decision diagram, okay? We will have relevance arrow, information arrow, function arrow, influence arrow, and direct value arrow. Okay, I'm going to explain each one of these 5 types to you so that you will have a clear idea of what they are. The first arrow we're looking at is the relevance arrow. So the relevance arrow is again exactly the same as a relevance arrow you would say in a relevance diagram. It represents a possible relevance between 2 uncertain nodes, okay? In order for an arrow to be a relevance arrow, it has to be origined from an uncertainty node, and then its destination needs also to be an uncertainty node. Need to come out of uncertainty, goes into uncertainty. Or in other words, an arrow that connect 2 uncertain nodes are called relevance arrow, and it represents the possibility of relevance. Okay. The next type of arrow is called information arrow. Information arrow is determined by the destination of it. Okay, as long as you have an arrow that is entering into a decision node, then you would have an information arrow. It could be coming from another decision node, just like over here. This arrow comes from another decision node, but it enters into another decision node. So this arrow would be an information arrow. It could also be coming from an uncertain node right over here. So this arrow coming from say going into D2 is also an information arrow, okay? Because it is going into a decision node. Also, you could have an arrow coming out of deterministic node and into a decision node. Then you would also have an information arrow in that scenario as well. So this is what information arrows are. Now, what it means, an information arrow indicates knowledge at the time of the decision, okay? For example, when we look at this decision diagram, we know that at the time when the decision maker is making decision D2, he knows what happened with respect to distinction C. He knows what kind of past decision he has made in decision D1. Okay. So this is what these two mean. And again, this arrow means that the decision maker knows what happened with respect to say for certain, okay? When making decision D2, the decision maker not only is having something extra in addition to the probability distribution of distinction C, he also knows what will happen for sure from distinction C. Okay. In terms of the weather, suppose this is the party decision and this is the weather distinction, then this decision diagram would mean that when Kim is making a decision on where to have the party, she would have observed what kind of a weather she would encounter for sure on the party day. And also this means when we have an arrow from decision D1 to decision D2, that means the decision maker knows what she has chosen, which alternative she has chosen in decision D1. The decision maker knows which possibility of distinction C has been realized. Okay. And the next type of arrow is called influence arrow. Okay, influence arrow are such arrows that it come out of a decision node and then goes into an uncertain node. It represents the fact that your decision will affect the distribution of the uncertainty. For example, the budget a firm puts into the marketing effort will affect the demand that the firm faces in the future. Also, in a previous example, the effort, how hard you have decided to prepare for midterm 2 determines how likely you will get a higher score in midterm 2. Okay, that sort of influence relationship is what we're looking at. Okay, I shouldn't say determine because, you know, even if you prepare super hard for the midterm 2, there is still a chance that you may end up with a low grade rather than a high grade. So your effort to prepare for the midterm is not 100% determining your grade. However, it does influence how likely you will get a high score in the midterm 2. So again, influence arrow is strictly defined as the special type of arrow that come out of a decision and goes into an uncertainty. And another type of arrow is called function arrows. It is the type of arrows that enter into a deterministic or value node, or simply put, an arrow that come into a double line shape, maybe an oval shape or a stop sign shape. Okay. It indicates the functional relationship, you know, going from E to F or going from D to F. An input in D determines the value of F rather than just influence it. Okay. Direct value arrow is the special type of functional value, a functional arrow that enters into a value node. Okay, so over here we would have these two, both of these would be called direct value node because they are entering into a value node. Okay, so here I want to make a quick summary about how to differentiate the arrows that come from an uncertain node. Say over here, this arrow comes from an uncertain node. This arrow comes from an uncertain node. This arrow also comes from an uncertain node. Well, how do we differentiate between among these three types? Okay, the first caution of notice is it is easy to be confused about the arrows that come out of an uncertain node. You need to look at where it is going into in order to differentiate them. If it is going into a decision arrow, you have an information arrow. That means the uncertainty is observed for sure before making this decision. If it is going into a value node or deterministic node, if it is going into a deterministic or value node, or if it is going into a double-lined node, then it would be the function arrow. Then that would represent the fact that the value, the uncertainty over here is going to determine the value over here. And then over here, if it is going into another uncertain node, that arrow simply means that the distinctions, the two distinctions are possibly relevant to each other. Okay, now we know what the nodes and arrows mean, then we can sort of put together some decision diagrams to represent various of decision trees that we have looked at, okay? So the next topic would be to look at several decision diagrams and try to interpret them or to correspond them, connect them with the decision trees that they represent, okay? Well, this is, the simplest decision diagram that you would be looking at. There is only just one decision in it, and then there's only one value in it, okay? Over here, this actually should be double-lined rather than single-lined. Now, this is a very simple relationship that you make a decision, you choose from some alternatives, and then the value of your decision is realized for sure. When you make the decision, you know for sure what kind of value you will get based on which alternative you choose. There is no uncertainty after you choose each alternative in terms of what kind of value you will get. This is not a very interesting decision diagram because, of course, all you need to do is to choose the alternative that lead to the highest value, okay? And here is the decision diagram for the party problem without any additional information other than the background knowledge that 40% of the chance is going to be sunny and 60% of the chance is going to be rain. Over here, we use this square node to represent this decision on the location of the party, okay? So this location square node represent the three alternatives for the location. And then we have uncertain. We are uncertain about the weather at the time of the decision. Why? Because after each alternative, you may have a sunny day, you may have a rainy day. That is what we mean. That is what we mean by saying that at the time of the decision, you are facing uncertain weather. Here, weather is represented by a round shape or an oval node to represent the uncertainty that we have about it. And then the value node, these values, $100, are represented by the value node over here, okay? So here when you have, as you can see, the value that a party gives to Kim is determined both by, is a function of both where it is and what kind of weather it has, okay? That's why we're using two arrows over here to connect the location weather to the value function. Weather and location to come together to determine the value. And since we do not know weather for sure when we decide on the location, so we cannot have an arrow from weather to location. Okay, the lack of arrow from weather to location represent the fact that we are uncertain about the weather at the time to determine the location, to decide on the location of the party. Okay, so again, these two arrows would be direct value arrows. That means once we have a location for the party, once we decide on a location for the party, once the weather, the two possibilities of the weather, once one of them becomes certain, then we know the value for sure. For example, if we decide to have the party outdoors, and if the weather turned out to be sunny, then the value of the party is $100. No uncertain about this $100. Also, if we know the location, if we have decided to have the party on the porch and the weather turned out to be a rainy day, then jointly those two observations will determine that Kim will have a party of $20 value. Porch, rain, $20. Okay, so these two arrows are direct value arrows. Again, it would be wrong to have an arrow from location. Well, it will be inaccurate to have an arrow from the location to the weather. In that sense, you are indicating that the location that is chosen by Kim has some influence on how likely the weather is going to be sunny or rainy. That is not true. Also, we do not have an arrow from weather to location because at the time to decide the location, we do not know what the weather will be for sure. Okay, so no arrows either from here to here or from here. This decision diagram represents this decision tree. We have looked at another decision tree that is more complicated than this one. That is, what is the decision like when you have already purchased the detector? Okay, over here, that will be represented by this decision tree. Okay, so again, in this decision tree, buying or not buying the rain detector is not part of the decision. Okay, this is just a snapshot, or this is just the decision to choose party location after the fact that you have been given a rain detector. Okay, the purchase decision, we will add that in the next part. But for now, let's assume that there is no decision to be made on whether you should get the rain detector or not. Okay. So of course, you need to have a node to represent this distinction, the rain detector's message, right? So that is what we have over here. Since in this decision diagram, you're not sure whether the rain detector will indicate it's a sunny day or a rainy day. That's why you're using a single-lined oval shape to represent the fact that the detector's message is uncertain at the time of the decision. Then after you read the decision, and then also, of course, there are decisions to be made in terms of the location. So here we have a location, and the square shaped node, the square shape of this location node represent this is a decision to be made. Also, we are uncertain about the weather. Also, we're trying to maximize Kim's party value. Okay, so compared to before, we're simply adding one other distinction called detector indication. You said before, we don't have that indication, detector indication distinction. Over here, we do have it because we're looking at this decision tree, which is more complicated than the previous one. Okay, so now we have, represented the nodes in these decision diagrams with two distinctions, with one decision node and with one value node. Now is the time to connect these nodes by arrows. Okay, the first thing we would notice is that at the time of the decision, at the time when Kim is choosing O or P or I, she would have known the message for sure, right? So that is why we are having an arrow from the detector's message to the party of location to represent the fact that when Kim decides on where to have the party, he has some knowledge, he has observed what the detector's indication is for sure, okay, At the time of the location decision, Kim is not guessing whether the detector's message is sunny or rainy. Kim has known that. The decision comes after reading the rain detector's message. Okay. And another thing that we need to make sure that we have is an arrow from between weather and detector distinction. Okay, this represents that we're looking at a detector that is relevant to the weather. Why? Because based on different messages of the rain detector, the probability of sunny day is changing. That is the definition of relevance between rain detector and weather. It actually doesn't matter if this arrow is from weather to detector or from detector to weather. It doesn't matter because relevance is a mutual relationship. It doesn't represent causal relationship. It only represents that these two distinctions are relevant to each other. Okay, and just like before, the value of the party is determined by the location of the party and how the weather is like. Okay, so we do not have an arrow from detector's indication, or we do not have an arrow like this. We don't have an arrow like this because really what determines the value of the party is just the location and the weather. Okay, the detector doesn't determine the value. Okay, so adding an arrow from here to here would not be accurate. So again, this arrow between the two distinctions, between the two uncertain nodes, would be relevance arrow. And this arrow would be information arrow because that represents the additional information that Kim has from the rain detector at the time of deciding the location. And both the decision, both where the party is and how the weather is like, jointly determines the value of the party. Again, look at that. When it is outdoor and sunshine, the value is always 100, no matter what message is, right? That is why we do not need to have an arrow from detector's message to value. As long as it is outdoor, as long as it is sunny, the value of the party is 100. As long as it's a porch party, as long as it is a rainy day, the value of the party is 20, no matter if the message is sunny or rainy, right? When you have a sunny day message, you have a porch party in the rain, the value of the party is 20. When you have a rainy day message, if you end up having a party in the porch in the rain, it is also valued 20. That is what we know. That is how we decide we cannot have an arrow from detector indication to value because the detector's indication doesn't determine the value of the party. The actual weather does. Okay, and these two arrows are just direct value arrows, just like what we have before. These two direct value arrows. And the next decision diagram is the same with this one, only except that we're not looking at a rain detector anymore. We're looking at a clairvoyant, okay? So over here, the message is clairvoyant, and the weather comes after clairvoyant's message. So here, we're no longer, well, what we can do is to change this detector indication into clairvoyant and then keep the decision diagram as is. That would be correct. However, we can sort of simplify this decision diagram once the detector indicates the weather perfectly. That is what the role of clairvoyant is, right? Clairvoyant says it's sunny, it is sunny. Clairvoyant says it's raining. It is raining. So in some sense, clairvoyant is able to help Kim to know the weather for sure before deciding where to have the party. That's why we're able to further simplify the decision diagram for clairvoyant from this complicated one into this simple one by noting that weather becomes certain based on clairvoyant's message. Again, we're able to do this simple decision diagram rather than this complicated one. The reason is that the detector is 100% accurate, which removes the uncertainty of the weather at the time of the location. Over here, the rain detector's message doesn't remove the uncertainty of the weather because after the message, there are still some possibility that the weather is going to be opposite, right? So these two are not 0 ones. Versus here, after clairvoyant's message, weather becomes certain, okay? Again, I want to stress that if you use this decision diagram to represent this decision tree, it would still be correct, okay? However, based on our further deeper understanding about the clairvoyant's message, we can simplify a decision diagram like this into a decision diagram like this. Here, we can just have an arrow from weather to the location because weather is known for sure before Kim decides where to have the location. When Kim decides where to have the location over here, he knows weather is going to be sunny for sure. When Kim is deciding the location after a rainy day message, he knows it's going to be a rainy day for sure. Okay, we know for certain. That is why we have an information arrow. Over here, we do not know weather for sure, so that's we don't have an information arrow over here. We're bypassing this detector indication, just connecting this with one arrow because this detector is 100% accurate. Okay. The next decision diagram is the most complicated one. Okay. This decision diagram and this decision diagram are based on the fact that you do not need to make a decision on whether to purchase the clairvoyant service or the rain detector. However, if you do need to decide on that, then you are facing this decision diagram, right? So before we're looking at this decision, we're assuming that you do not need to make a decision on whether to use or not, to buy or not buy the rain detector. Over here, let's put that decision into the picture, okay? First, you need to decide whether to buy the rain detector or not. That is represented by this node. Here, detector is a square node, which represent you have a decision to make here, whether to buy the detector or not. And then you, again, like before, you have the indication, you have the location, you have the weather, you have the value. Compare this decision diagram with this one. You have an extra node here called detector that represent the extra decision you need to make in this tree, which is whether to buy the detector or not. Okay, so here we have the 5 nodes to represent this decision, this uncertainty, these decisions, and the values, and also, of course, the weather. Okay, of course, now is the time to add in the arrows. We have a detector we have an arrow from the detector to the indication, it's because depending on whether you buy the detector or not, you will be either be able or not able to read the ring detector's message, upon which you can decide on the locations and everything else stays the same. So really, what changes is after we add the detector to here compared to this one, okay? We have an extra node called detector over here. These arrows will stay put. And then we have a detector over here. So what we need to do to decide is whether detector send an arrow here, 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 or here. Okay, that is what we have. Detector determines whether influences whether you will be able to read the indication or not. A detector will also, you will know whether this arrow represents information, okay? When you're deciding where to have the location, you know whether you have purchased or not purchased the detector. That's why detector is sending an arrow to location. Also, detector, the decision whether to buy a detector or not determines the value of the party. Because if you do not have the detector, your value of the party is $10 more. Why? Because the value of the detector, because the price of the detector are $10. Look at over here. If you do not buy a ring detector, an outdoor party in the sun is worth $100. If you do buy the ring detector, an outdoor party in the sun is worth $90 because you need to pay up the $10 cost. That is why we have an arrow from detector decision to the value node. However, detector, whether you buy the detector or not, doesn't influence how the weather is like, okay? The indication of the detector influence that is relevant to that. However, when you buy or not buy, it doesn't, when you buy the ring detector, you're not changing the probability of the weather. The message from the detector does. Okay. So that is why we have the 3 arrows. This arrow means impacts indication. It is an influence arrow, and this is a direct value arrow. This is an information arrow. Okay, so we have this decision diagram to represent this decision tree. This is the most complicated decision tree that we have looked at in this semester's classes, and you can succinctly represent this decision tree with this decision diagram. Okay. Just as in practice, let's look at another example over here. I'm not going to tell a story about this example. Rather, you can just take the example as is. And the question, we have 5 questions that you can answer based on this decision diagram. The first question is, are distinctions B and C relevant to each other given A and background knowledge? Well, you answer this question as you would before in the relevance diagram. Okay, just look at whether this condition is satisfied or not. First, look at whether this condition is satisfied or not. Meaning, is A sending an arrow to B? Is A sending an arrow to C? The answer is yes. Okay, condition satisfied. Now the question is, are B and C sending an arrow to each other? No. So the answer to this question is B and C are irrelevant to each other given background knowledge and the observation from distinction A. Okay, the second question is, can we reverse the arrow between A and B without other changes? Again, you would answer this question like you used to in the previous chapter about relevance diagram. The condition that you need to check, when you decide whether you can reverse the arrow between two distinctions or that are these two distinctions conditioned on the same information. A is conditioned only on background knowledge, B is conditioned only on background knowledge, and A. Okay, no other distinctions are sending arrow to either one of these two. So the answer is yes, you can reverse the arrow between A and B without other changes. Third question, are B and C relevant to each other given background knowledge? Again, start with the given part. Is this satisfied in the current diagram? Answer is no. C is conditioned on A and background knowledge. B is conditioned on A and background knowledge. So you cannot directly tell whether B and C are relevant to each other given background knowledge only in the current diagram as is. What you can do though is to manipulate the arrows so that B and C are not receiving arrows from anyone else except maybe from each other. Okay, the way to do that is first, let's reverse the arrow between A and B. We know we can do that from our answer to question B. So let's do that. And then we need to update this as, so now B is only conditioned on background knowledge. However, here C is still conditioned on A and background knowledge. What we can do is we can reverse the arrow between A and C as well. Question is, can we? No, because now A is conditioned on B and background knowledge, and C is conditioned only on A and background knowledge. So we cannot directly reverse the arrow between A and C. What we can do is, once we add an arrow from B to C, we can do this since it doesn't create a circle, right? So we can add an arrow from B to C. Now C is conditioned on A, B, and background knowledge. Now we can reverse the arrow. Okay, now we can do this. After we do this, C is conditioned on B, but not A anymore. So now we can erase A. So C is conditioned on B and background knowledge. Now A is conditioned on B, C, and background knowledge. Okay, so this is what we have after we manipulate the arrows so that B and C are conditioned only on background knowledge, not A, not D, not E, not value, but possibly on each other. Now the answer is, since we had to add an arrow from B to C in order to create this information condition, the answer is yes, B and C are possibly relevant to each other given background knowledge. Okay. Okay, the next question is, what does the decision maker know for certain when she's making decision D? Okay, let's locate decision D, which is over here. Now, uncertainty C is sending an arrow to D. So at the time of decision D, the decision maker has known what has happened to distinction C. Also, the decision maker knows what she has made at decision E. So these are the information arrows that we know. Both what you have chosen at decision E is no. What Uncertainty C has turned out to be is also known at the time of decision D. So that would be the answer to question D. Last question, is the decision maker's decision in E or D influencing A, B, or C? So again, the influence relationship is represented by an influence arrow, which means you need to check whether E or D has an arrow coming out of them and into either A, B, or C. Let's look at E first. Decision E is not sending an arrow to uncertainty A. That means decision E is not influencing uncertainty A. Similarly, E is not influencing uncertainty C or B because there's no arrow from E to either one of these three. How about D? D is not sending an arrow to A. D is not influencing A. D is not sending an arrow to C. So D is not influencing C. D is not sending an arrow to B. So D is not influencing B. Here, there is an arrow between C and D. However, the direction of the arrow matters in terms of the interpretation. Since the direction of this arrow is from C to D, this is an information arrow. If the arrow is instead like this, then that would mean decision D is influencing C. However, that is not what we have here. So the answer is no. Decisions E or D, neither decision E nor decision D is influencing any of these three distinctions, any of these three uncertainties. Okay, so be prepared to encounter such questions in midterm. Okay, just make yourself more familiar with